Yo, yo, yo! What's up, everybody? Welcome back. Today, we are working on trying to implement big matrix multiplications with OpenCL. So the context here is we are trying to well, okay, I wanted to track what food I'm eating, right? And so the natural evolution of that is it would be nice to, when I'm doing like ingredient entry in a meal, to like scan the things that I'm eating with like a barcode scanner instead of having to like type them into my phone because my thumbs are like greasy and shit from like touching butter or whatever, right? So then we started looking at doing barcode like parsing by hand. We overcomplicated the problem for ourselves. I'm very aware of this, but I do think that like I really want to like optimize for speed of scan. So like basically like making sure that we can handle like the most amount of errors, which means that there was like a bunch of image processing that we were doing that was like getting a little frustrating, a little hard, right? And so what do? We give up. We train neural network. Neural network parse barcode for me now. But before we can do that, we have to like figure out how to train a neural network, which means that we have to, build a neural network training framework. And if we're going to be training something to like process images, well, it's probably going to be kind of slow. So doing like GPU execution of this stuff is kind of nice. And so that's how we ended up where we are today, where we are trying to basically implement the amount of GPU stuff that we need to do in order to train a neural network for image recognition specifically. We don't have to be like super general, but being a little general is nice. So in the context of neural network training, you might have some like numbers, big list of numbers, right? Say we have like the typical neural network thing is you have like some inputs and you have some like hidden layers, they call them, basically like lists of numbers in here where you kind of like can attribute that each of these numbers like represents some sort of attribute, and you'll like stitch together layers of these numbers. God damn it, my scroll wheel's broken. And for each number here, you're going to connect to all of the numbers from the previous layer, and you're going to do some sort of like multiplication with those numbers and like an add at the end with some sort of like activation, right? So say like, and these layers can get pretty big. So say we have like, I don't know, like 1,000 things in one layer, and we want to like look at those 1,000 things and create a list of 500 more things after. Well, then this is like essentially what 5,000 or 500,000 numbers that you're going to end up with, right? So you're going to end up with like a box of numbers that's like 1,000 let me think, 1,000 wide by 500 tall. And you're going to take like your list of inputs to this thing, you're going to do like matrix multiplication on this to generate a list of 500 new numbers, right? So this is like 1,000 numbers here. This output is 500 numbers. And to do this, you have to like take each of the numbers in this list, multiply them by each row here. So like, we do this by this, this by this, this by this, and then we sum them all at the end. And so that sum part at the end, I think, is the interesting part of today's problem. Because if we're trying to do this on the GPU, right? And we're doing like, we're processing like a ton of these multiplications at one time, like these matrix multiplications, right? Because we're not just doing one of these, we're doing like as many as we can fit in GPU memory. We need some way to like sum all of these numbers on GPU, which is like weirdly not trivial. Surprisingly not trivial if you've never thought about it. Because like what you would do on CPU is you would like iterate through all of these numbers that you've multiplied together, and you would say, let me go, A plus B plus C plus D, and you just like accumulate them. But like GPUs are pretty shit at doing sequential things, but really fucking good at doing parallel things. And so we need to like come up with some way to implement this. Doing some Googling, a thing that you might do is you might try to leverage the parallelism of the GPU, and you might try to say, hey, every thread on GPU, just like add two of these numbers together. And then we'll take a bunch of threads and then we'll add like the outputs of those together, and then the outputs of those together, and the outputs of those together, and you can kind of do it in like, you know, log 2 number steps or log 2 elements steps, where you just kind of take like, you know, big list of numbers, some half of them, some half of them, some half of them, and then shrink them down to one number at the end. So we'll probably start looking down that line. I've been doing a lot of like reading. Okay, let's clarify that I started Googling about this stuff like yesterday, right? So my mental model here is probably quite wrong. But I think having a mental model of this is like important, because like how you write this code is kind of tricky. So I've been like Googling like, you know, I've been using CUDA resources because they're kind of like widely available. I have an AMD card, and OpenCL is not CUDA, but the concepts probably map relatively cleanly, because like at the very least, like AMD GPUs have a CUDA translation layer that like allows them to run stuff like the same code on their hardware. So we can probably assume that like it's similar enough that like you can do that translation. Architecture of GPUs that I've been reading about, they say that when you schedule work on a GPU, you're gonna be doing like, you're gonna be like, I have 1,000 numbers, sir, 1,000 numbers, and I would like to do an action on all 1,000 of those numbers. How does that get scheduled onto the GPU? Well, each thread is going to implement, like, he's going to run the program on one of those numbers. So there are threads. Threads are like too small of a unit of work for a GPU, kind of. They kind of want to do like lots of stuff at once, right? Instead of like having like a million CPU cores on that thing, they kind of have like less cores that kind of like do batches of work. So these guys get organized into blocks. Thread blocks. Which, hand wavy, if I understand what I've been reading correctly, get executed. A block is kind of like a thread on a CPU, kind of. Like a thread block will get allocated to a thing that they call like a multiprocessor. Multiprocessor. And like these guys kind of have like L1 cache on here. So there's kind of like memory that you have guaranteed to be like pretty fucking fast and shared between all threads in a block. Okay? Now there's these things that are smaller than thread blocks. Implementation detail, not really part of like the CUDA API. But like there's these things that they call warps, which sound very cool. Warps sound really awesome. But like your thread block might have like 1,024 threads or something, right? He might be able to execute like a lot of them at once. Or he might have grouped a lot of threads together. Note that this is not necessarily like, this is less than the number of things that you need to do for like a big list of numbers. So it's kind of like you take your big list, you chunk them into blocks, and then these blocks are allocated to these multiprocessors which have like shared L1 cache. Then within blocks, what I've been reading is that these guys are scheduled into warps, which basically say every thread in a warp, which is like maybe like approximately 32 threads, are literally executing the same instruction. So we like share an instruction pointer, and as we iterate through our code, we are all doing the same thing. We all have like our own, each thread has his own set of registers that he can store stuff in. But he's literally executing the same code at the same time as all the other things in a warp. Which is kind of interesting, because what happens if you have like an if condition in here, and like half the threads in the warp take the if and half don't? It actually just runs both the if and the else case, and just like shuts down the processors that it doesn't want running, or like the threads that are like didn't pass the check. Right? So hand wavy threads are like a thing that we can think about. Each kernel that we're executing is executing on a thread, but he has some sort of like shared memory with blocks which is faster than global. That's kind of like the extent of what we have to think about when we're writing this thing, but we should also think about the fact that like branches can be expensive because we're wasting memory, and also the fact that threads within a block will not necessarily be acting in lockstep, right? Threads within a warp are iterating in lockstep, but threads within a block are not, which is important because we might need to set up like some like memory barriers to make sure that if we want all of the information in a block to be like ready at the same spot, we have to like say, hey, wait for all of the other threads in this block to fucking finish, please. Okay, that's my mental model. Don't worry if you're like missing stuff, because I'm probably missing stuff, and also like it's fucking confusing. It's fucking confusing. Okay. But so I think plan of action is if we should just start with summing a bunch of numbers, maybe like without trying to do like multi-block synchronization, right? Maybe just say sum the amount of numbers that we can sum within one thread block. I think we can start there because that's like relatively easy. Then we'll have to like graduate to summing lists of numbers that can't fit in a thread block, right? Like we might have to start like doing multiple calls to the same kernel or something. I'm not really sure. And then so once we have like summing down, we should be able to like figure out matrix multiplication. But who fucking knows, man? Who knows? Let's just get moving and see where we end up. Okay, so let's implement some function, some numbers. Okay, he is going to take in our like OpenCL abstraction. Okay, and he's going to take in like lists of numbers, I guess. Maybe these will be GPU buffers. And let's think about like how we need to, like if we're trying to sum. Okay, yeah, let's just start with A as a GPU buffer and B as a GPU buffer. I think that will make sense. So we have two things on the GPU, and at the end we yoink out a floating point number. Yeah, let's do that. This is executor probably. Okay, so we actually probably need a kernel that we're gonna run this stuff onto. I guess like really this function should choose which kernel to run, right? So we might want to have some like OpenCL math or something. We need a better name for this thing. But this is going to be like maybe our abstraction around the idea of like this guy's going to have a function on him sum, and he will be like, oh, I have a kernel for this thing, right? So we can have like a sum kernel that's allocated here. That seems kind of reasonable, right? And he can know, hey, I'll call that kernel. Where kernel is you would hear this word and be like, are we talking about operating system kernels? That's what I would think. But kernel is like the GPU world's name for just like a thing that is executed on lots of stuff. A kernel of corn. Yeah, exactly. So I guess when we're going to initialize this thing with some like executor. And he is like this guy must be like responsible for compiling this sum kernel and sticking it somewhere. So let's make that thing. So we'll call this like sum CL, and we're gonna have to put some stuff in here. So for now, let's just put whatever kernel we had in here before. We had add. So this will add two numbers. It won't try to like. Oh wait, hold on. This is not two lists of numbers. This is one list of numbers. I'm a dumbass. Okay. So can we call this like sum program? He comes from sum CL. And on initialization, I guess we need to say this stuff will also live on an OpenCL allocator. This is like just like our own tracking data for like all of the stuff we've allocated with OpenCL, just so that we can like free in batches instead of trying to think about the lifetime of every little thing. And so this guy's job is gonna be like, can I create a program, okay, with this allocator and from the content of some program. Okay, pipe. And from this program, can we extract a kernel from this thing? Create, or is it program? Create kernel, okay. With some or something, right? And I guess for now, let's take our program that we wrote, sumCL. This guy says, hey, I am a kernel function. I'm going to be called sum. I'm going to take in a list of numbers from that. This list of numbers is like globally available to all kernels, not just the ones in my thread block, but every single one is going to look at these guys. And we're going to have some sort of global output as well. And I'm not sure what n here is. Probably number of numbers. Cool. And for now, let's not actually do the sum. Let's just say we'll just set output to the input or something. For now, just so that we have like something to look at. Okay. Let's see. We're gonna have to have some like buffers here. So can we do like temp alloc here is a CL alloc who, or maybe we like make our own. Sure, yeah, we can do that. We probably need our executor here as well. And here we can probably return our sum kernel. And our executor is executor. Okay, cool. So wouldn't it be a math program with a sum kernel? Maybe, yeah, could be. But for now we're doing it this way, because fuck it. I don't know what this is pissed about. Oh, I see. We can't use this twice, so can we go content? We'll call it. Okay. He's happy about that. Okay. So now we can just call like can we make like a new allocator here? I don't really know where we're going with this yet, but I think that we're going to need to be like allocating an output buffer to use with this guy. I think. Maybe not. I don't know. We'll see. I don't know. We'll see. Okay. This does look spelt wrong, huh? No, wait, that looks right. Maybe I'm high. Whatever, we'll see. So he's gonna say, I guess we're gonna like set arguments to this thing, right? So are these 1 indexed or 0 indexed? 0 indexed. So our first argument to this thing, Ice Leo, thank you for the 10 gifties. Much appreciated. Much appreciated. How kind. So the first argument here is going to be our buffers. So this is our inputs. And we are going to have to allocate a buffer for output, I guess. So we do something here. Can't you get the name of the argument somehow instead of using the index? Good question. Maybe. Maybe. Is this right only for now, I guess? Maybe it'll be read right later. And the size here, we're just gonna match a size, I think. For now. For now. The second argument, hold on. Second argument is the output. So here. And the third argument is the number of elements. Okay. Then we schedule this thing for execution. So we say executor, execute kernel, and we probably want to wait till this thing finishes. So why does this guy take an allocator? I see. It's where the events live on this guy. Okay. And then he must take the kernel. Okay. And what's he take? Number of elements. As a U size. Alright. That's fine. Then we wait for that thing. Maybe not, actually. We might schedule this thing and then read the output after. Yeah. So can we read buffer? There we go. And we are trying to read output into some CPU buffer. So can we say, let's allocate, this many floating point numbers? I guess that seems reasonable. So far, so good. And this is what we're waiting for. And then we can print this thing. Or return like, yeah, std debug print. The stuff from that we read back. Okay. And then unreachable because we don't know how to return this thing yet. Cool. Cool, 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 cool. Okay. So, can we call this somewhere? Boom, boom. Okay, so we should have like our... This is an OpenCL math initialized with our global CL allocator as well as our executor. And so then we can create this buffer of stuff, put some numbers on it, 1 through 1,000, sure. Works for me. And then can we call, maybe, yeah, we'll do this. CL math sum. Sure. Eventually this won't return a floating point number, actually. But we'll figure it out. So this guy, we send in A as well as our scratch allocator and 1,000. We're doing this for 1,000 elements. Okay. He's mad about some unused shit. All right. No function named sum in this guy because we have to try here. Error union is ignored. And what is this guy mad about? Probably this guy has to be tried as well. Okay. True. All right, there we go. Are we chilling? Okay, so he's mad at invalid value when we try to queue up a read. That's interesting. 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 How are we fucking that up? So when we call read buffer, he's calling CL in queue read buffer. OpenCL. Can we get like error logs? Like, can we ask for like, I think there's like some function you can call. To like set up debug logging. No, this is OpenCL. I want OpenCL. I'm pretty sure I saw something like this the other day. Weren't you getting logs back yesterday? On specifically for kernel application yesterday, I thought there was something like the like debug callback in OpenGL, but maybe I'm misremembering. In which case we can maybe just read this. He returns invalid value if the region being read or written is out of bounds or if pointer is a null value. Okay, what the fuck are we doing here? Okay, if the region is out of bounds... Am I fucking stupid? So this guy takes in... Like, what would the bounds be here? Oh, it's because A is empty. Because we never, fucking set A. So he's probably pissed off. Maybe not. Oh, maybe this is because it's write only. No. So he's mad at 645 read buffer. The fuck? So if I say the length is 0, does the same shit. Dude, am I high? The region being read or written is out of bounds, or if pointer is a null. So, value. So, presumably, it's not. Yeah, that's not null. Cool. So then we must be the region being read or written is out of bounds. Unless there's another time that this is returned as well. No. So out of bounds of what? Out of bounds of this buffer. How did we do this before? We had a write... Oh, size in bytes maybe. Yeah. Oopsies. There we go. Hype. Okay. Size is in bytes. Confusing. But now we do have what seems to be a list of numbers that increments by 1 every iteration. 0, 1, 2, 3, 4, 5, 6, 7. So that means that like the GPU successfully copied our input to the output. Hype. I've been meaning to send you something you might find interesting. One of my coworkers is working on compiling C, C++ to GPUs directly. He got Doom running on AMD and NVIDIA directly compiled from C. What the fuck? How? Like, you must mean something that's not... Like, you have, like, inputs to handle, right? So like there's something, it must be interfacing with like the system in some way. But I guess you mean like all logic running on GPU, which is pretty fucking crazy. That's super neat. Super neat. Okay, so we have numbers. Now we should try to sum them. So how do we do that? Oh, I forgot. We said we were going to start with a smaller list of numbers, right? Amount of numbers that could fit within one thread block, right? So maybe let's start with 16. I assume that fits, but I don't actually know. Can we ask what the local size is here? $256. 256. Now this is like kernel dependent, supposedly. But let's start there. So we should be able to fit const list size is 256. We'll say list size times size of floating point number. Here we can say list size here and here. So this should give us 1 to 256. Nice. Just another Discord? Hell yeah. I'll take a look later. Okay. So, within a thread block, we have, I think what I read that you can do is like, basically just iteratively within this thread block, stash shit in local memory. So like, we're gonna have, how do I draw this? We're gonna start with, 256 numbers in this block. A, B, C, D, blah, 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 right? And we can basically, like, iteratively just half the number of threads that are doing work, right? So we'll kind of start by reducing this down to, like, 64 numbers, then 32, right? Then 16, then 8, 4, 2, 1, right? Now, what sucks about that is you're kind of losing threads doing work as you chunk through this. But I guess, like, it's the cost of doing business, yo. There might be a better way, but this feels like, baby's first sum. Okay, how do you allocate local memory OpenCL? I can't remember if you have to pass it in or if you can like declare it as part of the kernel. Yeah, so these guys are saying you pass in local arrays and you set the kernel argument manually with a null pointer. So here we say like local float star temp, I guess we'll call it. And then when we call the kernel, I guess that means that we need to somehow call set arg with null. So can we just call this like local with size? So this is going to return size of length times size of CL float. Sure. So I guess we'll do the size stuff ourselves. So this is just gonna be like the size of this guy. Yeah. And here, this guy now turns into like one of these. And that means that when we call into our little abstraction, we should be able to be like, let's set argument 2 to local mem of some like scratch size. So here we need to like know, I guess, how big the local size is. So we need to query this thing, I guess. So where does like this local size come from? We call kernel work group size on the kernel. Which is a thing that takes in a kernel and a device. Okay. So get kernel local size or something. I guess. Sure. So he calls this stuff. Cool. Cool, and now we can call that externally now, so we can say like local size is get kernel local size for this sum kernel. Okay. And now this local memory is like the number of guys that can run times size of floating point. Right? I think that makes sense. I think. We'll see. I guess we do need to return this. And how do I want to do this? I guess just do an incast here. Fuck it. Okay, this guy's mad because I didn't write try here. Okay. Okay, so now we have some local memory that we can work with, theoretically. Theoretically. And so what we can do is I assume it's like get local ID or something. OpenCL get local ID. Yeah, here. Okay, so we say, give me my local ID. We're assuming we're working in one dimension right now. But this is chill. And so I guess we say like temp at okay. So we need to start with like some number of things, which I think I saw here you can get local size. Okay. So that's information for us that we can use somehow. And we have this many items. So I guess we say like there's probably like some loop that we do here, right? And we're probably I guess this is not how you do a for loop in this language. Oh, maybe it is, and this is just fucking set. Can we just set like file type equals C or something so that he's like less confused? We just need to figure out like what num steps is, right? Which I assume is like log 2 of the size, right? So if we have like 256 things we're trying to sum, this should turn into 8. So do we have like OpenCL log 2? Is that like a function that we have available to us? Yeah. Okay, cool. Math built-in functions. Sick. So we can do like you know, my fucking spacebar doesn't work sometimes. That's fucking annoying. Num steps is log 2 local size, right? And then okay. So how do we decide where we're indexing now? Right? So the first iteration, say we have 256 elements. We probably want to iterate through how do I say this? Each thread has an ID, right? So I'm thread 0, and I should sum element 0 with element 256. Wait, so we can actually... Yeah, and then thread 1 sums like 1 with 257. 2 can do like 2 and 258, right? Etc., etc., etc. Okay. Now, what's kind of interesting here is that it's the size of the buffer can actually be double the size of the thread pool, right? Because the first iteration should use all the threads available to us. So if we said we have one number per thread, then that's actually half the threads are going to do no work. So that's fine. So this should be able to sum up to 512 numbers. Okay, so I guess we say if... Hold on. So at the very least, if our thread ID is greater than n, or equal to, like the number of elements in an array, I guess we just do less than n here. Then we actually do the work, which is saying that like the temp buffer at our thread ID is equal to, I guess we first copy all of the global stuff section into local memory. Yeah, we have to do the first iteration first because temporary memory hasn't been like initialized yet. So the first iteration is that our thing is equal to global numbers at I, maybe. Not sure yet. Not sure yet. Plus numbers at I plus local size, right? Yeah. Sure. That seems like kind of reasonable, right? So we're saying like, you know, I'm global ID 0, and I am adding something from far down. Sure. So then for each iteration here, I guess this should also be like I less than n. This needs to be like global ID or something. And local ID. This will make my brain work better. Okay. Okay, so now we have an array of 256 numbers. Maybe. Maybe. And so on the first iteration, we look at if we only want to do like the first half on this iteration. So we say like if local ID is less than I don't know what here. Local size over something. Does it make more sense to do like I equals 1 while I is less than or equal to local size, and then each iteration we double I? That might make more sense. That might make more sense, right? Because then we can do over I here. Right? And then we can do like this output is what was in there before plus something, right? Like adding, like, so we're starting with global buffer. We add this number to this number over here. Then we have like, we're kind of like using this temporary buffer and like splitting it in half and adding this number to this number, I think. So this whole buffer size is local size. So if we do, maybe we like write this thing down. So like remaining size is local size over I. If local ID is less than remaining size, then we do local ID is local ID plus temp local ID plus remaining size. That feels kind of right. So interested in this? Is this their use of SRAM and summation? I think, I could be wrong here, but I think that this local storage is using like SRAM L1 cache shared by the executor that is executing this thread block. I think. But I'm not 100% sure on that. Okay. So then eventually, remaining size should be 1. And so we should only execute this on ID 0. And so at the end of all this, we should say if local ID is equal to 0, then we can put this shit in the final output. And we can do like output of the global ID over the local ID, maybe? No, we can't do that. Over local size is equal to temp 0. Right? Does that make sense? This tells us that, like, yeah, that does something. I don't know. We'll see. We'll see. I think this log2 is not used anymore. And so I'm hoping that this does something interesting. Oh, you know what we should actually do, though? Is, like, for now... Oh, that's fine. Let's just see where this takes us. Okay. So we got some fucked up numbers in here for sure, right? 2.83425E38. Okay. Can we actually, like, really scope this down? I want to, like, we should start really fucking small, I think. Like, start with, like, an initial list size of 4. And work our way up from there, I think makes sense. So I'm assuming, so we should get 1 plus, or 0 plus 1 plus 2 plus 3 should be our output, which is not, right? But it's probably because we're, like, looking at a bunch of garbage memory and using that in our sum. So we need to make sure that our, like, bounds checking is right. So here we're kind of assuming that the buffer is full, which is not really true. Right? If the number of elements in the array is less than local size, then, like, we should be doing something here. So, like, can we just look at n for now? I don't know if you can do, like, loops like this based off of an input variable like that. I don't know if that's, like, legal. Fuck. My brain is, like, not computing this stuff well. So we have, you know, a local size of, like, 256 numbers. But we only need to use the first 4 of them, right? And so we need to, I guess, choose our initial I based off of that. Yeah. We could do something like using the max of the local size, the like 256, and number of elements. We can use this information somehow, or the minimum. It's all legal. You can also hang the GPU, but the driver usually has default time for the kernel. Might not be a great idea during stream though. Got it. Got it. So this is like num elements. Remaining. Right? And I guess here we do this. Okay. I suspect that this will only work for powers of 2 initially. I don't really have like a good feel for why, but that's kind of how it feels for now. Oh, and there's probably some memory barrier shit that we have to handle here too, right? Because there's no guarantee that all elements within the thread block are like at the same spot. That's like a warp thing. So on every iteration, when we're expecting all of the data and memory to be the same, we should put like barrier here and here at the beginning, maybe just at the beginning of the loop. Yeah, we like here and then here, local ID 0 was the one who did this, so we only need a barrier here, I think. So how do we do like OpenCL memory barrier? Sync functions. Okay, so we set barrier with flags. For these functions, if any work item in a work group encounters a barrier, the barrier must be encountered by all work items in the work group before any are allowed to continue. And hype. If the barrier is inside a conditional statement, then all work items in the work group must enter the conditional. Oh, interesting. If any work group in the work group enters the conditional statement and executes... Wait. Must enter the conditional if any work item enters the conditional. Okay. If the barrier is inside a loop, then all work items in the group must execute that barrier on each iteration of the loop. Yep, makes sense. The barrier and work group barrier functions can specify which memory operations become visible to the appropriate memory scope defined by scope. The flags, yeah, okay. This is a bit field that can be set to 0 or a combination of the following values or together. When these flags are OR together, the barrier acts as a combined variable barrier for all this. So we just care about local, right? Global, we don't care about global memory or image memory. This stuff is all local. So we should just be able to be like, what's the difference between barrier and work group barrier? It's an alias. Okay. So I think we just do this. I think. As someone who works on GPUs for a living, always bench. Even if you can estimate small things and throw estimations off by a lot. Makes sense. Makes sense, makes sense. I think this is right. Maybe. I mean, it's at least more right than it was before. So here, num elements remaining is the same number for every single element in this work group, right? Because local size is for everyone in the work group. So is n, which means that this loop will execute the same for every guy in the work group, which means this barrier will be hit by everyone, which I think is okay. Okay, so that's... I don't know what I'm looking at here. So here, I was trying to output the result of this guy. So really only output 0 is valid here. So can we do this? Okay, and then this number, -1 E34, is like garbage. So what if we skip all of this? We just say, everyone put your shit in temp, and then if I'm ID 0, then copy that shit out. That should give us the number 1 or something, which it's not. Oh, it's because this first edition is fucking wrong, huh? Yeah, this is just wrong, right? It's just like reading invalid memory. Okay, cool. So this is the problem, is that our first iteration, we need to we need like some sort of like initial offset of the numbers that we're adding. So if we have 4 numbers, it's, you know, this over 2. Or the minimum of this in the local size, I think. Right, so if we have 4 numbers, we have 2, but if we have like 1,000 numbers, then this will be 256. And then here we have to check also, we need to check if, no. No, I don't think so. Maybe we just seed the initial run of the next stuff. Yeah. So, global ID is like where from numbers we are supposed to read. So, if... Oh, this is kind of interesting too. That, like, this kind of indicates that global ID can be in range 0 to n over 2, I think? My gut says that's true because we can, like, each executor only has to execute, each thread who runs can sum 2 numbers. Yes. So true right now. So true. Each thread that runs can sum 2 numbers. So he only needs to run n over 2 times, okay? So we should probably assume that every thread who runs is in the range 0 to n. Right? He's less than n, so this is always valid. Now, I think, like, where this might get hairy is if we add in our initial offset, then we might have a problem. Yes. Okay, we're getting somewhere. We're getting somewhere. So, if we have a range of, like, you know, 10, 24 numbers, we'll start with powers of 2 so because I can think of it a little bit. So my thread group can execute 256 guys, right? Which can execute 256 guys, which equals a sum of 512 numbers, right? Which means that hold on. We have, like, I guess it's that, like, thread group 1 will sum these numbers together, and thread group 2 will sum these two sets of numbers together. I think. But that's confusing because that means that we'd need IDs like 0 to 256 and 512 to like 768 or whatever with this like indexing scheme, right? If we're saying like look at like me plus the next work group over, that doesn't really make sense to me. We want something where we can give indexes 0 to 512 and some like segment all this stuff. So maybe it makes sense for us to start by summing with our neighbor instead of summing with someone really far away. Yeah, that makes sense. So our like initial index is global ID times 2, and then like initial neighbor is this. And then our initial sum is summing ourselves with our neighbor. Okay. Okay, that's something. That is something. Okay. So we run this, and we get our initial sum is 1, because we summed 0 and 1. Okay, cool. Now, num elements remaining is something. I feel like this is n over 2. I'm not sure though. So this is 4, n is 4, this comes down to 2, so then we do this 1 twice. So n is 4 here. We've already summed half the numbers, so we only have 2 numbers left to sum here, because we've already done the first iteration. Which means that this has to be less than for this to work. And so this should be index 0 and 1 that we get in here. So local size, is this also num elements remaining here? So here this is 2, 2, 2 over 1 is 2. So if local ID is less than 2, we do this sum. Yeah. And we sum him with the guy far on the right, because then we don't need to worry about like synchronization between threads. That's like a maybe. So now the workflow is we start with our global buffer, we take pairs of these guys and put him into a temporary array. Then we start doing like segmenting like this, where we kind of pull them for like this. And then we keep iterating down until we're empty. It's like a maybe. This number looks wrong as fuck. So I think I read somewhere that you can do like printfs in these kernels, which might be interesting. So yeah, I can just like printf. What happens if I do that? Whoa, it just fucking prints it. That's cool. So can we just printf like adding this to this? That's crazy. That's wild. That's very cool. I don't know how it's doing that, but... Oh, these need to be floats, probably? Okay. Cool. Okay, cool. So, here we can say adding numbers initial index to numbers initial neighbor. Okay. So this is the first iteration. This makes sense, right? We have 0 to 1, 2 to 3, right? Then we see that we're adding 1 to 1, which is bad, and 5 to 0. So this is the mistake here, right? This should be... I feel like this number of loops here is wrong too. Right? If we're trying to add 4 numbers together, we should only loop once there. Oh, fuck. Only log this on one thread. Okay, wait, that's something interesting. Can we, like, log, like, the full temporary buffer here? For 0, for int I equals 0, I is less than the number of elements remaining. Can we log, you know, temp buffer here is this? And we should be doing this with local ID or something instead of doing it in a loop. Yeah, this is like if local ID is less than num elements remaining, we print local ID here, and then this should tell us how much stuff is left, I think. Yeah, okay. And then we need to log this as float, not integer. Okay, so this is good, right? So the result of 0 plus 1 is 1, and the result of 2 plus 3 is 5. So that's really good. Really, right? That means that the temporary buffer at this point is, like, relatively correct. So it's here where we're doing something fucking stupid, right? So can we also log, this guy, like, ID this, which is less than this, is adding these two guys together. And then we can put in, like, local ID and remaining size here. So we can say ID 0, which is less than 2, is adding 1 to this. ID 1, which is less than 2, is adding 5 to this. So it looks like this is bugged. We're off by 1 here. Right? There should only be 1 guy left at this point. Num elements remaining is wrong here. I wonder if this is supposed to be n over 4. Because we've already halved it, and then we're halving it again on the first iteration. Yeah, it's kind of like this. Okay. But now this isn't happening at all. Less than or equal to? Okay, this is doing the right thing. Right, so we add the 0 to 1 into one index, Then we add 2 to 3 in the next index. We have 1 and 5, and then ID 0 adds those things together, and we get 6 as the output. Which is pretty sick. That's pretty sick. And so can we, like, I think we need to add, I wonder if this is, like, we need to make sure that, like, we're logging more correctly here. Nice. Okay. Cool. So I think that if that's working, we've summed, like, 4 elements. Can we up the list to 8 now and see what happens there? Maybe we should be writing some unit tests as well. Because this is going to be a pain in my ass. Yeah. So can we be like, move to CL and sum or something? Okay. Yeah. And that's gonna look something like whatever the fuck we're doing here. Okay. Okay. So we have... Oh, we need, this buffer is temporary. Uh-huh. Here we do an allocation instead. So this is like, oh, this thing already exists. So it's just like, here we take nums here, and then we need CL math here. I don't know. I don't know, man. I don't know. Okay, so here we should be able to be like, move to CL and sum with... I don't know. I don't know. Here's all our shit. And we call move to CL and sum with this guy, this guy, this guy, and what was it? It was like 0, 1, 2, 3, right? And I guess here, for now, we're just going to return the number. Sure. Sure. So far, that's looking kind of reasonable. Why is this guy mad? Int cast, probably. Okay. And then here we try, and we say, like, expect equal, 1 plus 5 is 6. Okay. Okay, so if I throw a 7 in here, this should fail now. Nice. Okay. Okay, cool. So now can we do 0, 1, and 2? Right? 3 numbers, which is not like a multiple of 2 or a power of 2, which it's neither of them, really. So this is going to be a little bit more interesting. Let's see if this also works. So, no. No, it does not. Okay, so can we now start like asking, can we put like a log parameter on this thing? Is that crazy? Or can we discard logs somehow? I don't know, man. We'll just put like a int log. And then and log is greater than 0 if log is greater than 0. Okay. If log 1 else 0. Okay. Okay, this is just for now. Just for now. Okay. Whoa, probably down here. Okay, cool. Cool. So this guy's just logging like jack shit, which is kind of interesting. Let's just make sure that this is logging at all. Hi, Mom, I'm on TV. Like, I do want to see some evidence that something is happening. Cool. And we can do, like, if local ID is 0 and this, then we should see this log exactly one time. Hi, Mom, I'm on TV. Good. And if I turn this off here, then we don't see it. Okay, cool. So we do see evidence that we were doing this in the 3-element case. And I suspect here that we are doing n over 4 is 3 over 4. This is returning 0. But we need to round this up, right? I guess that's the answer. Is we need some sort of like a round up to power of 2. Is that correct? Why do we need to round this up is the question that we need to answer ourselves. So we have 3 numbers. I would like to log what those things are. If log is greater than 0. Oh, we already have, can we just do this? Every single thing that ran should have put something into this temp buffer. Oh, interesting. No. If local, if initial index is less than n, and this is the condition where we put something in here. Right. So we got 2 guys in here, 1 and 2, and we're trying to sum the numbers 0, 1, and 2. Right. So this guy summed 0 and 1, and then this guy just took the 2 as is. Okay, so that's all good here. So then the question becomes, what are we supposed to calculate here? It's like round up to the nearest power of 2. Yeah, round up to the nearest power of 2, I think. Have to go now. Good luck with OpenCL, and if anyone else wants to talk to views, I'm clicking on the Discord. Later, thanks for popping by. Thanks for popping by. Yes. Because we have... Dude, I have to, like, think through it so slow because I'm so fucking stupid. But it's like... We have 1 and 2 in our buffer. And we want to sum those. So this is simple, which means that we want to run this iteration 1 times. And if we do n over 4, that gives us the wrong number. So why did we have n over 4? It was because we had the same sitch. So n was 4. 1, 2, 3, 4. And we wanted to run this iteration 1 time, right? Because we had already summed, we had already kind of collapsed this into a set of 2. And so we needed 1 more iteration to collapse that down. Now, I feel like whatever the fuck we're doing here is like a stupid way to do that. I can't really like place it, but it feels wrong. So I guess it makes sense. Yeah, so we're halving twice, but then we want to round up. That's the answer. Half twice, but round up. So we want like maybe like some sort of like seal div or something. Right? Which is like what? You want like 1 over 4. You want 0 out of 4 goes to 0. You want 3 out of 4 goes to 1. And you want 1 out of 4 goes to 1. 4 out of 4 goes to 1. So I think you just add 3 and then divide. Right? So this becomes 3 out of 4, which goes to 0. This becomes like 6 out of 4 goes to 1. 5 out of 4 goes to 1. 7 out of 4 goes to 1. Yeah, so you just add 3. Num int denom. So this is like return num plus denom minus 1 over denom, I think. And then this is probably both of these, seal div local size 2 and seal div n4. Almost certainly, right? Okay, yeah, nice. Nice. So that solved that problem. So now both our 4 element list of 4 and our list of 3 add correctly. Let's do a list of 1. Right? Just to be confident in the degenerate case. Good. Okay, and then can we upgrade to like, I guess what we should do is like 4 like list sizes is you know, 4, 3, like we have 1, 3, 4. Then we want to do like work group size. So can we get like local size is executor get kernel local size given CL math sum kernel. Okay, so can we do like local size times 2, local size time like 2 plus 10 or something? Yeah, let's do this. Let's do this. And let's try to test all of them. So for list sizes size, let's generate the list. So I guess we should do, it's fine. Yep. For 0 to vowels, I guess for 0 vowels land, yeah. vals I is equal to I. And then we just need to say, like, expected is what? There's some formula for this, right? It's like, sum 0 to n. 1/2 n times n plus 1. Size times size plus 1. This. Okay. Float from int here. Incompatible types here on expected. And then I guess this means that we shouldn't actually be doing expect equal here. Expect approx equal. And then what is it? It's like tolerance here is the last element, so 0.01 or something. Okay. So now can we go back to the ones that we expected to pass? 1, 3, and 4. Okay, we're back to being broken, which is not good. Not good. Why is it broken? Temp buffer 0, 0. Adding 0 to 0. Expected? Yeah, we should be 0. No? Size? Yeah, wait, what the fuck? If my size is 1... Oh, is this to n minus 1? Yeah, I think this is probably wrong. Because if this is size 1, then we expect the answer to be 0. So this should be... Yeah, then why does this... What is this formula for? Sum of 0 to n, I guess that means n is included, because it would be 0 plus 2 over 2 is 1. So do we do this? N. Lower limit 0. Like... Oh, oops. Sum... I mean, I guess it's just the same thing, right? Dude, am I stupid? What do we do here? Easy. Perfect. Why do math when you can just not do math? I'm a genius. Okay, there we go. So these 3 pass, and now we can throw in a local size here. Use NixOS, yep. Yep. Okay, so that's good. That's good. Even if we huck in local size there, we're chilling. Now, local size times 2 is gonna should also work, right? Because we can fit, you know, if our local size is 256, then we can sum 512 elements without going out of bounds of our work group. But this doesn't work, so that's good. Not good, I mean, but we can try to figure out why. Why is this... Wait, what the fuck? Why does that change anything? Am I stupid? Like, this is failing on the... Whoa. Why is it inconsistent? How do you do, like... Okay. So that's interesting. Adding 0 to -1 here. Okay. Okay, wait, that's interesting. So... yeah, we do not zero out the VRAM. That is true. It could be, we're probably here adding to something out of bounds, right? We're saying ID 0 is adding 0 to -1, right? Which means that he's adding, like, he gets in an input list that says 0, right? He puts that 0 in the temporary buffer, and then there's just kind of like garbage in here. Then he thinks that he needs to add in, you know, like, the adjacent number here, probably. And that's freaking him out. Right? It's the remaining size here. He's seeing like 0 less than the remaining size is adding this. Okay. So why is it like this? One is like the degenerate case, but like we might be doing, I think it's because it's like rounding up from 1 to 2 because that's the next power of 2. Or whatever. Yeah, he's rounding up this way. This is also kind of fucked up. This is like multiples of 4. This is wrong. Surely num elms remaining should be a power of 2. Surely. 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 It must be. Like, it must have to be. But that's not what we're seeing here. So we're seeing that we have 1 over 4 is getting seal dived to 1 instead of 0. So we're seeing, we're going through the first iteration of this thing. Now that's because in some cases, if you had like 7 out of 4, we want this to go to 2 because we have 2 iterations to do to take these 7 numbers and put them down into 1 number. Is that right? Because you have like... Okay, let's pick a different case. Dude, my poor little brain is like really struggling to understand this. Okay, so we have 4 numbers, or 3 numbers. 1, 2, 3. We do our initial add. So we take 1 and 2. This is 3. And then 3 comes in. This 3 comes here to 3. Now this 3 doesn't get added to anything because like there's only 3 elements. Then we take this list size 3 and we divide it by 4. This rounds up to 1 because we have to do 1 iteration to merge these 2 numbers together. Okay. So that's why this is wrong, is because if we had two numbers here, we would already be done here. Nothing left to do. So I think that this needs to be uh, like div round up pow 2. Okay. And so it's like, so we have 1 out of 4 needs to go to 2. 0 out of 4 needs to go to 0. No, sorry. 1 out of 4 needs to go to 1. 2 out of 4 needs to go to... Am I fucking stupid? Am I fucking stupid? I might be fucking stupid here. Dude, it's like my brain is not wired for this. It's crazy. It's really fun, actually. Okay, so we have two numbers. We, on our initial iteration, merge those down to one number. Nothing to do. So, 1, 1. 2, 1. Okay, we have three numbers. 1, 2, 3. This comes down into two numbers. So, this is 3 has to go to, we have like two sets of numbers to do it with. 4, 2 numbers. 5, 3. 6, 3. Is that true? 1, 2, 3, 4, 5. This comes into 1, 2, 3 numbers, which takes how many iterations now? Yeah, this is num elements remaining. Yeah, what am I doing, dude? It's... Okay. Oh, but there's like a divide by 2 happening here again. Right. Okay. We can draw it again. 1, 2, 3, 4, 5, 6. This gets summed down into like 3, 7, and 11. Right? Which means that we want to iterate 3 plus 11 and 7 plus nothing to come down here. Right? So this should be like 14 and 7 after. Yeah, so this should be like iter, like some lms to some or something. And then what is this for loop for? Dude, my brain cannot handle this. So here we're saying for... I almost feel like we should start with like remaining iters, or like remaining, like, I need a name for like half remaining. Yeah. So like temp size over 2 or something like this almost, right? Yeah. And then temp size here is n over, like, the minimum of local size over 2 and n over 2. Right? No. I don't think that's right. Okay, so we start with numbers 1 through 5. 1, 2, 3, 4, 5. We turn this after initial iteration into 3, 7, 5. So our temp size here is 3 from 5, right? So here, if n is 5, we want like a ceil div here of n over 2. And maybe this should be like, actually like temp size is ceil div min local size n. 2. Okay, that's getting me somewhere, right? So if we have 5 elements that come in, this will be like 5 over 2 sealed is 3. Sealed div 5 over 2 is 3. So this is going to be 3 now, which makes sense. While I is greater than 1, and we like divide by 2 over and over again, okay, yeah. And we might want a ceil div here as well, and here. I'm not really sure. I think so. I guess here, at this point, is guaranteed to be a power of 2. And it is here as well. Or so this is, or sorry, this is guaranteed to be even. But I guess this could be like 3, actually. This could be like 3. Which means that, yeah, if we're dividing by 2 and we don't start at a power of 2, then we have to ceil div the whole way down. I think. I don't know, that seems kind of reasonable to me. Okay. So then, we say if local ID is less than half remaining, we print half remaining here. Okay. And maybe that makes sense? Failed to compile because num elements remaining. True. So while half remaining is over like 1 or something, maybe 0. Hello? It's right here. Am I stupid? Oh, I think I need to build because it gets embedded. I think that this is iterating forever. Right? Which is bad. Which means that, like, this guy is always getting down to 1 or something. And, like, rounding back up to 2. Okay, let's just do this for a second. I don't think this is right, but... at least, hopefully this goes back to passing for elements, you know, lists of size 1, 3, and 4 or something. Hopefully. I don't think it's consistent still. Yeah, it's still not consistent. Because here we are adding 0 to 1 again still. It's still not right. Okay. So you come here, we get n here is 1. We have one element. We are trying to, so this should be 1. Can we print that? Yeah, this should be 1. Okay. So then this guy comes down here. He gets half remaining. Is ceil div 1/2 is 1 again. And that shouldn't happen. So I wonder if this is temp size over 2. And then can we also like pre-jack this temp and can we pre-jack the like temp thing just to like really fuck shit up if we're doing the wrong thing still, if we're like ever accessing invalid memory? At least now we will know. Okay, that's promising. So if we go back to like, I think this should be consistently right now. Can we do like for I in 0 to 1,000, do this, done? How do you do this? Bash for loop. How the fuck do you... Where's like the fucking range? You put squigglies? Yeah, and then can we do like do zig build if this then break else if this then break else done? How the fuck? Oh, it's like this maybe? If for this do zig build if this then break done? What the fuck? Oh! For this do done. Oh, there's yeah. Wait, there's yeah. Then like bash if. Oh, it's fi. Okay, so this does seem to be working. And then can we go back to like fucking this up intentionally? Yeah, okay. Cool. Yeah, nice. Okay. Can we go back now to trying to try some extra juicy cases? Local size. Okay, that's chilling. Local size times 2. Okay, here we go. Shit not working again. Shit not working again. Okay, so this is surely just on can we say whether or not we want logs here? Yeah. Then here we can go like like this. Three, four, local size times 2. And then can we do like params size is param 0 and log is params 1 and then throw a log here. Okay, so we should see what's CPS about? Because this thing is it should be like this. There we go. Okay. And then can we just only log on the last one? Cool. Okay. I guess we just start looking at what he's logging. Okay, so this is bad news bears, right? We're seeing a bunch of people talk about that, like, sentinel number that isn't supposed to get touched, right? So, why is this happening? So, off rip, we're seeing... am I missing something? If local ID is this, we print the temp size. Then, if initial index is less than n and log is greater than 0, then we print temp buffer equals. Okay. So it's weird that, like, we're not seeing anything in the temporary buffer. Right? We're not seeing any of these. Right? Which kind of lines up with the fact that this stuff isn't running. So initial index is global ID times 2. And global ID times 2 plus 1. Okay. So our local size must be quite large here, with our global IDs higher, like also quite high. Oh, because we're only supposed to queue this for half the size of the array. Right? So we're supposed to do sum here takes in the size here. And we're supposed to run this shit as size over 2, I think. No. Yes. Right, because we're supposed to only run for half the element. So probably like a seal div here as well. I think it's like this. Okay, round up doesn't exist because this lives somewhere else, I guess. Okay, so good news, I think, is that that goes back to passing everything but the last one. I think. Can we go back to, where's our list sizes here? Delete the list size times the local size times 2. Yeah, okay, we're back to everyone working. Forgot to delete over 2 somewhere. No, I think I want this. This was intentional. I was trying to say round up to the nearest multiple of 2 and then divide that by 2, which is like the same as like a seal div. just because that's like the stuff I have here, right? To say like, if I have 7 elements in my buffer, execute 4. You know what I mean? Because like the first iteration is like trying to partition, you know, these guys or something. I don't know. There's like 4 iterations that have to be run on the first iteration. Like, yeah. Round up, div by 2, first iteration. Okay. Sorry, it's hard to express because I don't have a good mental handle on it, and it's just hard. Okay. So, we can go back to this log, though, and see if he's still doing, like, brain-dead, stupid, fucking stupid stuff. Right? Which, it looks like it's less fucking stupid now, right? We can see now that he's not, like, how do I say this? He's not, like, writing 99999 everywhere anymore. He's like, these are valid numbers so far. Right? And then these all look like valid numbers too. So the question is like, how did we fuck up now? So we can kind of see the sequence of operations that he's doing. He's running up to 255 here. And you can also see the out of order execution of the thread blocks, which is kind of hype, right? So we can see that we ran thread block with like 64 sequentially up to 128, right? Then we ran 192 to 255. Then we ran 160 to 191. And okay, can we look at the global IDs here too? So we're not seeing any of the like big global IDs anymore, which seems kind of bad. That seems kind of interesting. I would think that like, so the fact that global ID and local ID are always the same here is very strange to me. Oh no, I guess that's true actually. I guess because our global ID, we're still only executing enough things that can fit within one thread block. So the global and local IDs should just be the same. Okay, hype. And so if we are queuing up, how many things are we queuing up here? 256, right? No, 512? What is our local size? Yeah. So we have 256 things. 512. Yeah, so we have... We started with 512 items, I think. Hold on. Am I fucking stupid? Yeah, so we start with 512 elements. Okay. And we end up with temp size 128. Because we take the minimum of the local size over 2 and n over 2. I think we need a times 2 here. Right? Because we can handle up to local size times 2 elements. Nice, we're so back. Okay, that works now. That works. So now we can at least sum as much stuff as fits in a single thread block. We should probably like try some like, you know, -7 or something and like -1 or something. Right? Just to like, I don't know. It just seems like the type of shit that could be wrong. Right? So like might as well check. Yeah, that's funny. Okay, so like these guys work. Everything, the perfect multiple works. Going off by 7 does not seem to work. Interesting. Interesting. All right, what's the kernel fucking doing then? How's he fucking it up? So we end up with temp size 253, local size 256, and 505. Okay, so we have 253. We had 505 elements, and now we are trying to we've handled half of them, and to coalesce those together, we have to run 253 more iteration. Like we have 253 more elements, which makes sense, right? Because it's 5. That would times 2 is 506, so that handles that. So then we should start seeing everyone up to like. So all these temporary buffers are just like correct, okay? Then we are adding while we're less than 126. Then while we're less than 63, 31, 15, 731. Huh. Interesting. What am I missing? Okay, can we try to reproduce this failure with like smaller numbers? You know what I mean? Like I want to know if we fuck up at like 9. You know what I mean? That was a good guess. Right? So 8 probably works and 9's probably broken. Okay, hype. This is like an easier way to debug this then. Okay, so we're expecting with 9, there's like a few enough numbers that we can like piece it together. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We're expecting 1, 5, 9, 13, 17. 1, 5, 9, 13, 8. Oh no, it's okay because the 9's not part of this. So that was actually correct. Because it's 9 elements, so 9 is not included. Of course. Okay? So then we should be seeing add 1 to 9. So that's these guys. Great. It means that we're off by 1. Half size here is supposed to be 6. 1, 2, 3, 4, 5 plus like blank. And he should be adding 1 to 13, 5 to 8, 9 to blank. And he's not. Right, which is why this seal div before felt like it was right. But this didn't work in other cases. Okay, and then this is interesting too. Right, so now we're seeing 1 to 13, 5 to 8, like we wanted. But then 9 to 9,999.99, right? And it's like, what the fuck is going on there? It's... I mean, it's because this is using that as well. Yeah. Interesting. Interesting. So this bounce check needs to be different than this guy. So it's almost like remaining is what we should be tracking here. Okay. Half remaining is... Yeah, so we need like some case here where it's like if the local ID Yeah, it's like if local, oh yeah, we have like half remaining. If local ID is less than, or this should be like execute limit or something. We seal div this so that it so we do some copy unconditionally. Except we don't have to copy things if there's no add. Because they're already in the right spot. Because like if we have like 1, 5, 9, 13, 8, right? We want to add the 13 to the 1, the 8 to the 5. The 9 passes through, but there's like nothing to add it to. Right? Yes. So that means that the execute limit is just remaining over 2. Yeah. And I guess half remaining is a better name here because it's the adder here as well. Okay, so we have 1 to 9, which is wrong again. This is like add offset and execute limit. Okay. Let's try that. Okay, so we have 1 to 13, correct. 5 to 8, correct. 9 passes through, which is hype. And then we should have what? 14, 13, 9 at the end. We add 14 to 13, which is great. Right? But then the 9 is lost here. So why is that happening? What am I missing? It's this condition is doing something stupid, right? So we start with remaining equals temp size. I want to do something like this. Okay, so we start with a temp size of 5, and then our size here should be 3, not 2. So which makes me think that this should be a seal div. I guess. Nice! Nice, nice, nice. Here we go. So now this is like 5, 3, 2. So then we add the 14 to the 9, the 23 to the 13, and everyone is fucking chilling. Everyone's chilling. Okay, so now the question is, did I break something else, right? So this stuff all used to work. Hype! And then I bring back local size times 2 minus 7. Hype! Hype! Local size times 2 minus 1. Nice. And then here is going to be an absolute fucking shit show, but I think that it won't work if I do local size plus 1, right? Because we can only sum within one work group right now. So I like it's like almost certain that this fails. Yeah. Because once we get outside of a work group, we fall the fuck over. Because we have no way, like the output we could probably make it so that we can sum on CPU the last step pretty easily. Right? If we did like output global ID over local size equals temp 0, then looked at an output of 2 parameters, I think that would give us something probably sane. I think. Whoa, 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 where's my output buffer size? Out CPU comes from output. What is he pissed about? Why can I not ask for 2 elements out of here? Our output should be like fucking mega big. So I don't really see why this should be a problem, but yeah, what the fuck? Oh, because size is sometimes 1. I see. Fuck it. I mean, in reality, we should just put this as like 2 times float 32, and I bet you that'll work. Okay. So in the case where this is like fucking broken, this is not within the tolerance of this. And the question is if we add these 2 numbers together, if that's close. Not quite. Not quite. So it's not as simple. Not as simple as just taking what we have and outputting it where we want it to go. But I think my fucking brain hurts. It's 2 hours into stream, and so unfortunately, I think we actually have to call it here, which is crazy. Because we didn't even finish implementing sum a list of numbers. All we've done is sum a list of numbers that can fit within one work group, which is, you know, the subsection of the global list that shares one set of cache. So, I guess that's a problem for tomorrow, is trying to figure out how to like extend this to, basically like we need to re-trigger these sums again, I think, to like take the list of outputs that we make and sum those together. And we probably have some sort of limit. Eventually, we're going to have to make this an interface that goes like, we're going to have like 100,000 numbers and we want to sum like, you know, sets of 9 of them together or something. Or like maybe a more realistic is like sets of, you know, 7,000 or something, right? So we're going to try to get the GPU to eventually create a list of like 1,000, this 100,000 over 7,000 list of summed numbers, but it's a problem for later. It might be useful to look at the generated OpenCL from something like TinyGrad. I agree. I would like to start doing that soon. All right. Cool. Thanks for watching, guys. If you like what we saw, we stream most days. We're aiming for 12:30 to 4 o'clock Pacific time. It's 3 now. For this GPU stuff, we might end up being a little shorter because like my head hurts thinking about it. There's like too much reading and like brain melting to like kind of like I have to like switch the whole way I think about programming, which is like good. But anyways, we'll be back tomorrow. Aim for 12:30 Pacific time. There's a YouTube link in the Twitch description. Some subset of VODs go up there, some don't. The rest go up on Patreon, on Twitch, or on YouTube members, where you can like sub in the appropriate place to get the rest. We do that because the stream stops happening when I run out of money, and so it gives us something to give back to people who want to contribute to the longevity of the stream. Otherwise, okay, I think that's all we got to plug. YouTube, peace out, and Twitch to find someone to raid.